So today I'm going to talk about the sun and how it's a source of energy and light, how energy is produced in the sun, the products, the process, the reactants, and we're going to talk about a little bit about the sun itself. So the sun is a star. It's a very medium-sized star actually, and it's one of the billions and billions of suns in our solar system and in our galaxy and in our universe, because there's a ton of them. So it's the center of our solar system, and it takes up about 99.8% of the mass, of the total mass of the solar system. Of course, the other 2% is Jupiter. This is Earth compared to the sun. It has a mass of nearly 2 times 10 to the 30th kilograms, so that it's pretty heavy, and it has a surface temperature of 5,778 Kelvin. So it's really hot. It's made up of mostly hydrogen and helium atoms and some heavier atoms as well, atoms that are actually found on Earth. It has an internal convection motion, which means that it produces an electromagnetic field. Just like the Earth, the sun has layers. The core is very dense and very hot, and those are conditions that are ideal for nuclear fusion. Right above the core is the radiative zone. The energy moves through via radiation through this zone, and right above that is a convection zone, and this is where gases mix and cause like a very granulated pattern on the sun's surface. And that's why when you look at the sun through a telescope, you can see that it looks very granulated. Even in this picture here, you can see the convection zone is also where sound and pressure waves are produced. So the sun does make noise, and it's very loud. The sun's atmosphere starts with a photosphere, and here that's where light and energy begin to radiate. The radiation here is absorbed by heavier atoms also found on Earth, which means that the sun isn't just made of hydrogen and helium atoms. There's actually normal material with mass inside the sun, not just hydrogen and helium. Right here you can see the sunspots, and these are darker regions, and they're not darker because they lack light. They're darker because they're colder. They're cooler than their surrounding areas. So you can see where it's where the sunspots essentially lay. Right above the photosphere is a chromosphere, and right above the chromosphere is a corona. So the chromosphere is kind of odd because here the temperature increases with altitude. With the sun, the core of the sun is the hottest part, and then the corona is the coolest. But the chromosphere is kind of weird because here the temperature actually increases with altitude, so it's hotter as it gets more outward into interplanetary space than the core. And then right above that is the corona, which is the outermost surface of the sun, and it goes out into interplanetary space. Here it emits UV and X-ray radiation, which, by the way, does reach Earth. Unfortunately, well, actually, no, fortunately for us, UV and X-ray radiation are blocked by our ozone layer. And so it's very important that we try to preserve that to keep those dangerous rays from giving us skin cancer, because those are dangerous. The sun's actually an average star, as I've mentioned before. So in a few thousand years, eventually it's going to run out of hydrogen and it'll turn into a red giant. And then after a red giant, it turns into a planetary nebula. Oops, sorry, I did something. And then after that, it turns into a white dwarf. Bigger stars, more massive stars, turn into red supergiants and then into a supernova and either a neutron star or a black hole. Fun fact, Marvel's Thor, I'm a comic book fan. Marvel's Thor, Mjolnir, his hammer, is actually in the lore, it says that it's made out of a neutron star, and that's why it's so dense and it's so heavy and only Thor can pick it up. But I thought that was a pretty cool little fact. Supernovas are very, very, very bright stars. This is what a supernova looks like from a telescope. Their masses are being pushed outward, so it's an explosion. And it has an energy output of 10 to the 44th power joules. This is also where nuclear fusion occurs. The elements produced through fusion in a supernova move at very high velocities. and so they're actually more energetic. There was a scientist that said, in my reading, that said that we are made of star stuff because the iron in our blood is made from iron that's created from supernovas out in space. So I thought that was pretty cool. I think his name was like Adam Howell. He's one of the sources that I did use for both my paper and my presentation. Nuclear fusion occurs in the core of every star, and the essential idea is that the nuclei have two atoms of smaller elements fused to form a larger element, and the product would be energy. For the sun, it's mostly hydrogen to form helium, but more nuclear fusion can occur to form heavier elements on the periodic table. That's how they're created. So in the process, first, you have to understand what an atom looks like. There's a nucleus. In the nucleus are protons and neutrons held together by nuclear forces. These forces are stronger than the electrical forces that hold electrons together on the outside. That's why the atomic number is the number of the atomic number is the number of protons an atom has in its nucleus. If you change the atomic number, you're changing the element. Hydrogen is one proton. It has an atomic number of 1. It has 1 proton and 1 electron. So 2 hydrogen atoms will form a deuterium atom. A deuterium atom is an isotope of hydrogen, and it has a mass of 2. And that's because it has 1 proton and 1 neutron, forming a mass of 2. Most of the mass is concentrated in the nucleus, and that's why it has a mass of 2. The product of this, of course, is energy. Then that deuterium atom will fuse with another proton, a hydrogen atom, and create a helium atom, which has a mass of 3 and an atomic number of 2 because it has 2 protons. The product of this is energy, and some neutrinos also fall out of there. Nuclear fusion requires a lot of heat and pressure, and that's why the core is ideal for this to react, for this reaction to take place. One of the products is, of course, energy. With the sun, it's a form of gamma radiation. This is the most energetic. This is your UV radiation that's blocked by the atmosphere. But as you can see in the chart down here, that gamma radiation goes through paper, through skin, through steel, and even through lead. So it's very energetic and is very, very low wavelengths. Alpha particles and beta particles have less energy, and those are those are particles that we deal with on a very daily basis. Another form of energy is heat and light in the form of photons, and the output for the sun is 96 billion megatons per second. Less than 1% of the sun's mass is converted to energy. The rest are all helium atoms. Here it says greater than, but I actually meant less, so less than 1% of the sun's mass converted to energy. Another product is called neutrinos. These are subatomic particles that don't have a charge. They're produced normally during radioactive decay, and they pass through the sun's interior in only a few seconds in comparison to energy, which takes several thousand years to pass through the sun's radiative zone. Excuse me. Studying neutrinos gives scientists information about the energy output of the sun. So these are very, very important particles. Applications. The picture on here on the right is a nuclear reactor for CERN. CERN is a science organization that study a lot of particle and atomic physics. And nuclear fusions occur in the core of the sun, but they can be replicated in the lab. And some applications are, of course, weaponry and electricity. What do I mean by weaponry and pyrotechnics? Well, the hydrogen bomb is a nuclear fusion reaction. And how it works is that a deuterium atom, which I've mentioned is an H isotope, is struck by high energy neutrons. So it creates this large, quick blast of energy. In November of 1952, Mike is the first hydrogen bomb set off in the United States down in, I think, New Mexico. And this is what really started the whole Cold War, Red Scare, the competition for the nuclear arms race. This was it. Here's a schematic for what a hydrogen bomb looks like. And the general idea is that this part right here are deuterium atoms, and then this part right here is what causes the this to explode once they clash together. So it creates this large, massive explosion. Another application is electricity. These are produced by nuclear reactors. These guys right here are nuclear reactors. They control a sustained nuclear reaction. And in 2007, less than 20% of U.S. electricity is powered by nuclear power plants, which is pretty cool. The great part is that nuclear energy is actually cleaner than burning fossil fuels and coal. So that's a big bonus. Unfortunately, the reactants are very radioactive, and the wastes are really difficult to neutralize, and so it does cause some pollution as well in that form. The Chernobyl tragedy is an example of what could happen if nuclear reactors explode. In Chernobyl, Ukraine, in April of 1986, one of the 4 nuclear reactors that powered the city exploded due to some design error, and the result was devastating. Radiation waste spread for hundreds of miles, and it was a major nuclear catastrophe, and a lot of people either died, mutated, got cancer, and a lot of them even today suffer from those terrible effects. And it covered a lot of the northern part of Europe. There was another one called the Thousand Island Mile tragedy, which is a similar event or occurrence. So in conclusion, the sun produces energy that we need to survive. Without the sun, we won't live. Well, we probably might, but not as long. The nuclear reaction that occurs is nuclear fusion. It occurs in the core, and essentially it's 4 protons that fuse to create helium and energy and other atoms from other elements. Hopefully in the future, with science and technology constantly improving, getting better, better uses for nuclear energy can be discovered, and maybe we might even find a way on how to neutralize the wastes from nuclear fusion reactions so that we can use nuclear energy as like cleaner energy, greener energy. So that is my presentation. Here are my references. The guy that said, the scientist that I got the saying from was Andrew Howell, by the way. He was the one that said that we are made of star stuff. Well, he had a quote from a guy that said that. But yeah. So if you have any questions, just shoot me an email. And thank you so much for listening. Have a good night.